All right. So chapter 8, which is what we're going to be starting today, focuses still on that topic of alkenes. All right, but now we're going to take a deep dive into alkene reactions. And we sort of already started this discussion last week when we were talking about alkenes. We talked about their properties, and we talked about two reactions of our alkenes, and we're going to learn quite a few more in this week as well. And what I'm going to start to do here is to create like a master list of these reactions. Basically, we're going to have a bunch of details in our notes, but we want one place that we can look that kind of summarizes all of these reactions. So that's what I'm going to start here is my master list for these reactions. And I'm going to leave a bunch of space. So we covered two of them. So we're going to put those two down. And then I'm going to leave a bunch of space down here. And I want you to do the same thing in your notes so that we can fill these in as we cover these reactions one after the other. All right. So the first one that we learned about already is what's called a hydrohalogenation reaction. All right, so let's put down an example of a hydrohalogenation reaction. Here's my alkene. Hydrohalogenation, so a HX here, where X is one of our halogens, chlorine, bromine, or iodine. All right, and everybody take a second and give me what the product would be of this reaction. All right, so if I color these carbons about that carbon-carbon double bond, we're going to do an addition reaction where I add a new bond to each of those carbons. All right, and specifically, which one is my halogen going to go on, the orange or the green? Orange. That more substituted carbon gets our halogen. The other one gets our hydrogen. All right. So in addition to having like a list with the title of the reaction, we got our sample reaction here. We're going to make a note of the important features of these reactions as well on the side. So first of all, for some reactions, we have our reaction mechanism. And this is an example where, yes, we have a reaction mechanism, or we should know our reaction mechanism. And we're going to note that mechanism is characterized by that carbocation intermediate. All right, as we noted, y'all told me that we had to put that halogen on a specific carbon. That is what we call regioselectivity. And this reaction does indeed have regioselectivity. That's why we put that halogen on our specific carbon. And what did we call this kind of regioselectivity, where it goes on the more substituted carbon? Markovnikov. So we're going to note that this is a Markovnikov reaction. And then there was a third property that we were going to look out for, which was called stereoselectivity. And this reaction here, because of that carbocation intermediate, because that carbocation intermediate is that flat trigonal planar structure, the incoming nucleophile can attack it from either side. So you're always going to get a racemic mixture, meaning this reaction does not have any stereoselectivity. We don't select any specific stereoisomer in our reaction. All right, so this is this master list that I'm talking about creating. For each reaction, we're going to give a sample chemical equation here, and we're going to make note of these important features that we should know about these reactions. So there were two that we covered. One of them was a hydrohalogenation reaction. The other one was a halogenation reaction. All right, so let's get a cyclohexene here. And we're going to hit it with one of our diatomic halogens. All right, so this was a reaction that, again, we had a reaction mechanism for, but it did not have that same carbocation intermediate. Instead, it had this cyclic intermediate. And that cyclic intermediate was an important consideration. Before we talk about why that is, let's just remind ourselves, do we have any regioselectivity in this reaction? Do I have to be careful about which carbon I choose to make my new bond to, like I did in this one? No, why not? I don't know if I heard it. Same bond, right? We're making the same bond on both carbons, so I don't have to be picky about which one goes where. So our regioselectivity here is none. All right, but because of that cyclic intermediate, okay, let's just kind of go back and remind ourselves, looking at this reaction mechanism. We formed this cyclic intermediate here, and because of that, that nucleophile has to attack from the back side of that cyclic structure. It cannot attack from this front direction here on the same side of that bromine. This wouldn't work. It's got that ring in the way. All right, and so because of that backside attack, we had this stereoselectivity. Where we're going to have to make our two new bonds on opposite sides. So if we take our cyclic structure here, and I'm going to add those bromines on there, or those halogens on there, I'm going to put one of them on a wedge structure, but the other one's got to go on the opposite side, on a dash. All right. This is what we call an anti-addition. Anti-addition meaning our new bonds are on opposite sides. All right, and I have to be careful here. I didn't leave myself enough room. I got to shrink this down. Because I'm not just going to get one product here, I'm also going to get its enantiomer. So I'm going to have to draw this one as well as its enantiomer, where I take those wedges, flip them to dashes, and I take my dashes and flip them to wedges. All right, now this anti-addition is the stereospecificity of this reaction is the hardest part of drawing your products, for sure, right? Again, it's very easy to tell where your new bonds are going to go. It's much more difficult to tell which direction those new bonds should be pointed and whether or not we should have one or two structures. All right, so we're going to pick up with examples working on this stereoselectivity of these reactions. And we're going to sort of cover all of our bases, look at all of our possibilities, and that's summarized in these 4 examples really well. All right, so everybody take a minute. Let's copy down these 4 examples so we can compare and contrast what our results look like for each one. All right, so how are we supposed to get our stereo-specific products for these reactions here? So let's focus on this first one. All right, importantly, how many carbons should I have in my product? The 5, right? Same as what I have over here. Make sure you always are counting carbons. We're not going to lose any carbons in this reaction. So I'm going to start off with my 5 carbons here. I know I'm creating a new bond on either side of my alkene, my carbon-carbon double bond. All right, but again, those new bonds need to be pointed in opposite directions. So I'm going to make one of those bonds a wedge, and I'm going to make the other bond a dash. All right, but now I have to be good, and I also have to include my enantiomer for this product. All right, so everybody take a second and draw its enantiomer. Gonna flip our dashes to wedges and our wedges to dashes. All right, so here are my 2 enantiomers. All right, and so to be clear, why do I have to include my dashes and wedges? Because we only got a small subset of the stereoisomers produced. All right, everybody take a second and assign RS stereochemistry to this orange stereo center here. I'm going to work on this one. I want y'all to work on this one. All right, assigning R or S stereochemistry. All right, so what do we get? This one would be 1, 2, 3. We're going in a clockwise direction. Do we have our normal rules or our flipped rules? Normal rules, so this would be R. And y'all can just trust me that this one down here is S. So then what would be the stereochemistry of its enantiomers stereocenters here? S and R. All right, so then let's just note here, what was not produced in this reaction? What stereoisomers of this 2,3-chloropentane were not produced? I have RS and SR. What am I missing? RR and SS, right? So what are not produced here are RRR and SS product. That's why we have to draw these stereo-specific products, because I'm missing certain stereoisomers. So I want y'all to take a second and play the same game with these next 2 structures down here, our 4-carbon alkenes. All right, so I got my products here by playing the same game. I put one chlorine on a wedge, the other one on a dash, and then I drew its enantiomer by flipping my dashes to wedges. I played that same game in both of these examples here. All right, but this is a good illustration of when we have to be careful. One of these is correct. I need two structures. The other one, though, is incorrect. I've drawn the same structure twice. All right, I shouldn't have included two structures as my product. All right, so I want you to look carefully and see if you can't figure out which one we've drawn twice here. All right, so let's look. If I take this molecule right here and I just rotate it upside down, are we convinced here that we have the exact same structure drawn twice? All right, so the problem is I wouldn't want to include this second one here. And what is it that's special about this structure that means that I only have to include it once? The fact that when I drew my mirror image, I actually had the same molecule. It's a meso compound. All right, so this one here is a meso compound, meaning that its enantiomer is not a distinct molecule. Rather, its mirror image is not a distinct molecule. It's just the same molecule drawn twice. So, first of all, let's take a look at our model kits and see if we can't convince ourselves that this is correct, that this is indeed a meso compound. All right, so everybody first, let's just convince ourselves that what I've built here is that first structure drawn. Well, it's not up there anymore, but that structure that I had drawn where that first chlorine is on a wedge pointed out at me, and the second chlorine is pointed back here on a dashed bond. All right, remember meso compounds have that plane of symmetry. It's really hard to see that plane of symmetry in this particular rotational state. But remember, we're always rotating about our carbon-carbon single bonds. So if I rotate around this bond here, I'm not changing my molecule at all, right? I didn't make or break any new bonds. And all of a sudden, I can see that plane of symmetry much more easily going down the middle there, all right? So indeed, that first compound that we drew is a meso compound. If we rotate about that bond, we can see that plane of symmetry really easily. If we do our next structure here, right, this is now the next one, where again I have my chlorines pointed in opposite directions, you'll see there is no such plane of symmetry. These chlorines are on opposite sides. Even if I rotate this thing around, I still don't have a plane of symmetry here. I can't fold this molecule in half and have it be the exact same. So this one's enantiomer is going to be a distinct structure, meaning that I have to include them both. All right, but these were really, really similar reactants here, right? The only difference is that this was the E2-butene and this was the Z2-butene. One of them led to a meso compound and the other one didn't. So what's like an easy double check that I can do to test whether or not I have a meso compound? All right, well again, everybody take a second and assign this chiral center R and S, and I will do this one down here. All right, this orange is an R, this other one is an S, and that is important because meso compounds are always RS, which is why their mirror images are also RS. If we played that same game down here, we would find that this compound is RR, meaning that its mirror image is what? SS. So those are indeed distinct molecules, all right? So if you're looking at a molecule and you're like, ah, man, I feel like maybe it's symmetric, maybe it's not, I'm having trouble seeing it, go ahead and assign RS stereochemistry. If it's a meso compound, it has to have RS stereochemistry, right? The other enantiomer, or my other isomer of my 2-butene, will instead produce the RR and the SS of my compounds. All right, so yes, so for this one, I have to include both of them. For this one, I'd get marked some points off if I included both of them because I'd have drawn the same structure twice. I just need one because it's a meso compound. All right, and then let's do this one here. Okay, let me just show you real quick what not to do. Okay, what I'm going to play the same game, right? I need to put a chlorine on a wedge and a chlorine on a dash. All right, but there's something very wrong with the way that I drew this compound right here, or rather about this carbon right here, my orange carbon, which is that this no longer is representing that tetrahedral structure. Remember, why we do our dashes and wedges is to represent this tetrahedral geometry of those carbons. Oops. All right. Importantly, if I have two carbons, or two bonds rather, that are in the plane of the page, that means the other bond needs to be sticking out at me and the other one pointed to the back, right? So in order to draw our tetrahedral structure, I can't leave this methyl group here as a straight line. I have to put it on whatever the opposite is of my chlorine. It's got to go on a wedge here. Oh, whoop, not a chlorine. Just a methyl group. Okay? But even then, this is overkill. Because if I'm going to assign R or S stereochemistry to this orange carbon right here, what am I going to find? It's the same, right? So what is it? RS, or a trick question? Trick question, right? This isn't a chiral carbon at all. So I don't need to show any specific stereochemistry. I can just draw my straight line bonds, right? No stereospecificity of that carbon. So I'm just going to draw these both as regular bonds. Right? This is a chiral carbon, so I can show my stereospecificity. But again, I'm going to get this and its enantiomer. And since there's only that one chiral center, I get a mixture of my, what's this one, S and R stereoisomers. And when we have a 50-50 mixture of all of our, or rather equal mixture of all possible stereoisomers, what do we call that? A racemic mixture. And since we have a racemic mixture, we have all of our possible stereoisomers represented, unlike these other cases where we noted that we were missing particular stereoisomers. Here I got everything. I'm not missing anything. So instead of showing my two stereoisomers, I'm going to show that this is a non-stereospecific product by just putting that other chlorine on a straight line bond. All right, so our racemic mixtures we represent with just those straight line bonds. We don't have a stereospecific reaction, or rather a stereospecific product. All right, so we got all these possibilities. Sometimes we have to include two structures with dashes and wedges. Sometimes we only have to include one structure with dashes and wedges. And sometimes we don't need dashes and wedges at all. All right? So let's just make ourselves a little bit of a reference here for, do I need to worry about stereochemistry? All right, when do we have to include those stereospecific products? So first, we want to ask ourselves, well, is the reaction stereospecific? All right, as we noted in our cheat sheet already, we got two reactions. One of them, the one that we've been working with, our halogenation reaction, is stereospecific. It's got that anti-addition stereospecificity, but the other one isn't. So if I'm talking about a hydrohalogenation reaction, I don't need to worry about dashes and wedges. That reaction is not stereospecific to begin with. All right, so first of all, is the reaction stereospecific? If no, then no, you don't have to worry about it. But if yes, then we're going to have to move on here. All right. Then we want to figure out how many stereocenters are produced. Because if you'll note, in all of these examples here, when did we have to worry about our dashes and wedges? When we had two stereocenters that were produced, right? So we got three different options here. First of all, you could just have a reactant where you don't make rather a product that doesn't have any stereocenters at all. So if it has 0 stereocenters, then that molecule is simply not chiral. So you don't have to worry about it. All right, what about when we get 1 stereocenter produced? That was the case for this last reaction, right? We did have a stereocenter that we produced, but what do we get when we just have 1 stereocenter? That racemic mixture. In both of these cases here, you would just use those straight line bonds. All right, but if we do make 2 stereocenters, then we're going to produce specific stereoisomers. All right, I'm going to even say a specific subset of stereoisomers. All right, so if there's 2 of them, that's when we're going to make sure to include our dash and wedge bonds. All right, and even when we need our dashed and wedged bonds, we had these 2 different examples here. Sometimes we were supposed to draw 1 structure, sometimes we were supposed to draw 2 structures. So lastly, on our little reference cheat sheet here, let's ask, all right, we know that we need dashed and wedged bonds. How many structures? Well, if that was a meso compound, then we would just have 1. If it's not a meso compound, we're going to need 2 of them. Okay, and this little reference sheet here will work for all of our stereospecific addition reactions. Like I said, we're going to learn more reactions as we go throughout this week. And so this is a reference here for when we need to be worried about our stereochemistry. Cool. All right, so we reviewed here and added to our cheat sheet our halogenation and our hydrohalogenation. Like I said, I'm going to leave a bunch of room here to add more reactions. All right, and so now let's start going through these new reactions. Our first one is what's called a hydrogenation reaction. All right, another addition reaction here. We're going to take our alkene our simple alkene substrate, but this time our reagent is going to be hydrogen gas, or H2. All right, and given what we've discussed about addition reactions up until this point, I want everybody to take a second and predict what product we're going to get from these hydrogenation reactions. All right, so what are we adding to either side of our, what used to be our carbon-carbon double bond? Hydrogens. So then what's our functional group of our product here? An alkane. All right, so this is how we can reduce this carbon-carbon double bond to a carbon-carbon single bond, turning our alkene into an alkane. All right, you may have heard of hydrogenation before with hydrogenated oils. All right, that's where they take those very healthy unsaturated fats and they hydrogenate them to make the delicious but less healthy saturated fats. All right, but this is this hydrogenation reaction, adding H2. In order to better understand what's going on here, we're going to look at what we call an energy diagram. You might remember these from Chem 1B. Where we're going to make this little graph here. Where on the y-axis we have thermal energy, and on the x-axis we have what we call reaction coordinates. And this is how the energy of a reaction is changing, or how the energy of a system is changing as a chemical reaction occurs. All right, over here on the left-hand side of our graph, we have our starting energy of our reactants, which in this case, as we said, are our alkenes. And on the other side, we have the end energy of this reaction, the energy of our products, which again we said are alkanes. All right, and so what we'll notice is that our alkenes are higher energy than alkanes. All right, that's what our diagram is showing us here. Going from reactant to product, Alkanes are lower in energy than alkenes. So this reaction is favorable from the standpoint of where we're starting and where we're ending. It turns out that the energy that you have to put in to break that hydrogen-hydrogen and carbon-carbon pi bond is way less than the energy that you get back out when these two new bonds are formed, right? So there's this net release of energy. We have to put some energy in to break these bonds, but we get a lot more out when these new bonds are formed here, all right? So this reaction would be favorable from what's called the thermodynamic standpoint. Okay, this reaction is thermodynamically favorable. We decrease in energy as we're hydrogenating our alkene. All right, we talked about thermodynamics a lot last semester. Remember, the only thing that matters in thermodynamics is where you're starting and where you're finishing. So if I'm going to look here at this energy level of where I'm starting with my alkene and then where I'm ending with my alkane, all right, the difference here is the delta H of this reaction. And again, this reaction is releasing energy, so it's thermodynamically favorable. All right, but our energy diagram here, it also tells us what's happening to the energy as a reaction is occurring. And in order to get converted from reactants to products, we got this energy barrier here that we have to jump over. Does anybody remember what we call this energy barrier here? The activation energy. Awesome. All right, so now if I'm going to look from where I started to the height of that barrier here, this is what we call our activation energy. And what does your activation energy tell you about a reaction? Does anybody remember? So definitely the amount of energy, right? We kind of think about our reaction as being this little marble here. And in order to get from the reactant side to the product side, it's got to jump over that barrier. But if it had a really small barrier, it'd be easy to jump over. If it has a very large barrier, it takes a lot more to get over that. And that corresponds to the kinetics of our reaction, right? How fast or how slow a reaction occurs. And this particular reaction has a very high activation energy barrier, right? So this reaction has a large activation energy barrier. Which means from a kinetic standpoint, it is very unfavorable. Okay, so this reaction here, if we have an alkene and we introduce hydrogen gas to it, from a thermodynamic standpoint, yes, it really wants to form that alkane product, right? The equilibrium very much so lies in favor of that product, that forward direction. The problem is that it is prohibitively slow. And I'm not meaning like, oh, you got to wait till the end of the day slow. I'm meaning like you need to wait until the end of the century kind of slow, right? Impractically slow on a time scale of our lives. So we have this way in which we can speed up a chemical reaction. Does anybody remember what that is? Catalyst. Awesome. And so this reaction here, it's not just going to require hydrogen. It needs some sort of catalyst as well. And there are these two metals that they use, platinum or palladium, that will help speed this reaction up on a reasonable time scale. All right? So this reaction here requires a catalyst, either platinum or palladium. And truthfully, there are a few others that you can use, but this is good. We don't need to go crazy. All right. So if I'm going to be good here, let's show this is our energy diagram in red of the uncatalyzed reaction. If I'm going to show the energy diagram of my catalyzed reaction, importantly, I have to start and end in the exact same place, right? Catalysts don't change the energy of your reactants or products. They don't change the thermodynamics of the reaction at all. All they do is provide an alternative pathway with a much smaller activation energy. Right? So here's my activation energy of my catalyzed reaction, which is much smaller than the activation energy of my uncatalyzed reaction. Okay, and so this particular reaction is one that we're not going to have like a full mechanism for. I'm going to note what an important feature of having those metal catalysts, platinum, palladium, these are metals, right? So they're going to be like a big chunk of metal that you throw into this reaction mixture. And what happens is the hydrogen actually bonds itself to the surface of that metal catalyst. And then your alkene comes along and we have our addition reaction. All right? Because of that surface chemistry, that means that both of those hydrogens are going to be added to the same side of that double bond. Okay? So this is what we call not an anti-addition, but rather a syn addition. Right? Our new bonds will form on the same side instead of opposite sides like what we saw for our anti-addition. All right, so then let's go ahead and now that we've talked about this reaction, we're going to add it to our list here, add it to our summary list. All right, I'm going to be strategic with my substrate that I picked. It'll help illustrate this this syn addition. All right, so when I do my syn addition here, I'm going to put these two hydrogens on the same side. So they're both going to be on wedges or both going to be on dashes. All right, but then I got to be good. What am I going to have to do to those methyl groups? I'm going to have to put them in, change them to wedges, absolutely. So they have to be on the opposite side of where those hydrogens are. And I want everybody to take a second and to try to tell me whether we're going to need to draw a second product or whether we can just leave it at this one here. Right? Is this a meso compound or is this not a meso compound? What do we think? This is a meso compound. We can see our plane of symmetry right down the middle here. You could also convince yourself that you have RS stereochemistry about those two chiral centers. So yes, our cis isomers can be meso compounds. Our trans isomers cannot, but our cis isomers can. All right, and let's go ahead and make our list of these features. Okay, our reaction mechanism. As we said for this one, no. We're not going to have a full-blown reaction mechanism with electron pushing arrows. We can note it's that solid state catalyst. But no, we don't have any reaction mechanism. All right. What about regioselectivity? Is this reaction going to be regioselective? No, why not? Right? We said that this one was regioselective and this one wasn't, and now we're saying this one isn't. Why not? Same bonds, right? So it doesn't matter which side I add my hydrogen to. I'm adding my hydrogen to both sides. So our regioselectivity, no, we don't have any. But our stereoselectivity, yes, this is a syn addition. All right. Our syn addition is when we have new bonds on the same side. All right. So we covered a new reaction here, our hydrogenation reaction. We talked a little bit about it, and then we added it to our list here. So now moving on, we're going to discuss what's called a halohydrin. All right, formation of a halohydrin. So what the heck is that? All right, so again, we like to start out with our easiest case scenario, our simple ethene. So in a halohydrin formation, we're going to use a halogen. But we're not just going to have a halogenation reaction. We're going to introduce that halogen along with another nucleophile, water. And what we're going to get is an addition reaction. We get a bromine on one side of our carbon-carbon double bond. But on the other side is not going to be another bromine, but rather a hydroxyl group, an OH. All right, and this molecule right here that contains both a halogen and a hydroxyl group is what they call a halohydrin. All right, so let's try to understand why we get this halohydrin formation here by looking at our reaction mechanism. All right, and the very first step is going to be exactly what we saw for our halogenation reaction. So everybody take a second and see if you can't remember that first step in our mechanism for our halogenation reaction. All right, remember that carbon-carbon pi bond can play the role of our nucleophile, kicking off that bromide leaving group. But then the weird thing here is the bromine also attacks, leading to our cyclic intermediate. All right, we discussed that cyclic intermediate in our halogenation reaction. We get that same cyclic intermediate in our halohydrin formation reaction. What's also produced at that first step is that bromide ion. And previously we saw that bromide ion playing the role of the nucleophile in that second step, right? That's what came down and attacked this carbon and opened this ring up. But now we have water present. And the way that they do this reaction, bromine's actually not very soluble in water. So you have a little bit of bromine and a ton of water molecules floating around, all right? So because we have so many more water molecules, what's going to play the role of a nucleophile in our next step is one of those water molecules, all right? So my water molecule now is going to be attacking that carbon and opening up that ring. All right, so everybody take a second. Draw me the product, following these electron pushing arrows, draw me the product of that first step. Second step, rather. All right, so this would be a bond breaking arrow. That pair of electrons is going to become a lone pair on that bromine. All right, but if I look at my other carbon here, what type of arrow is this? This would be a formation arrow. So now that lone pair on that oxygen is becoming a bonding pair. All right, but we can note it's still got those two hydrogens bonded to it. All right, I didn't break any bonds on that hydrogen. So if I'm being good, I then have my 3 bonds. So that means I have 1 lone pair and a positive charge. And if we look, we're almost there. We're almost to our product for this reaction. All right, I'm just going to need to do what? Yeah, definitely. So I'm going to need to take off this hydrogen here. All right, now, if you said the bromide ion is going to do it, I would understand, because if you did a balanced chemical equation here, HBr would be your other product. But let's think about it. If we have water and bromide ions mixed together, which one's a stronger base, water or bromide? Water, right? Bromide is an absolute crap base. That's why its conjugate that's why it is the conjugate base of hydrobromic acid, one of the strongest acids that you can have, that you're ever going to see in the wild, like pKa -10 or some crazy crap like that, right? So the bromide ion is an absolute crap base. So really, if we're being good, what's going to happen in our reaction mixture is a second molecule of water is going to be the one playing the role of the base, deprotonating that, so we'll produce some hydronium in the process. We don't really care about those inorganic products. We just care about our organic product. All right, so we have this mechanism here. We see it's really similar to our mechanism for our halogenation reaction. Just what's taking place in that second step isn't the bromide being the nucleophile, but that extra water molecule that's in that reaction mixture. All right, and given this step in our reaction, what would we say about the stereospecificity of this reaction? Is it a syn addition, an anti-addition, or do we not have any stereospecificity? All right, just like with our halogenation reaction, this backside attack here is we can't go this direction with our oxygen attacking. It's got to go from the backside here. So just like before, our cyclic intermediate lets us know that we have an anti-addition. This is indeed a stereospecific reaction. Okay, but what about the other one, our regiospecificity? All right, I'm adding a bromine to one side and an hydroxyl group to the other side. So is this reaction going to be regiospecific or not? Are my bonds the same? No. So yeah, it's going to matter whether I put the bromine here and the hydroxyl here, right? This would be a different product than if instead I had this as my product. So yes, we got to worry about our regiospecificity. All right. I'm going to be lazy and not show the full mechanism here, but I am going to sort of show our intermediate. That cyclic bromonium ion intermediate. All right. But rather than drawing it like a perfect equilateral triangle, I'm going to draw it like more like what it would really look like in solution here. If we could shrink down in our magic school bus and look at it. Okay, it turns out that it's not this perfectly symmetric structure. This bond over here is already starting to break. All right, my bromine is preferentially going to go on this other carbon because this bond here to my more substituted carbon is already starting to break. Because since it's more substituted, it's more stable at holding a partial positive charge. So that means my nucleophile, my water, is going to specifically target that more substituted carbon. So my product here will have the bromine on the less substituted carbon and that hydroxyl group on the more substituted carbon. All right, my water is going to attack that more substituted carbon. All right, and we had that fancy word for something when it prefers a more substituted carbon. This is a Markovnikov. All right, but specifically we're going to note for that hydroxyl group. All right, it's that hydroxyl group that's going to go on that more substituted carbon. All right, so let's go to our summary sheet here. Let's add our next reaction, our halohydrin formation. All right, and as we noted here, this is a reaction that we did our reaction mechanism for. Again, had that cyclic intermediate. Okay. We did have that regiospecificity. All right, we said it was Markovnikov for that hydroxyl group. And we also had that stereospecificity for this reaction. It was an anti-addition. So kind of the worst of both worlds here. Not only do we have to worry about our regiospecificity, we also have to worry about our stereospecificity. So we're going to pick a specific example to put on this little chart here that's going to illustrate both of these. All right, our methyl cyclohexene, 1-methylcyclohexene. All right, everybody take a second and give me my products that we would expect from this halohydrin formation reaction. All right, so first of all, we got to be good about where we put our new bonds. In terms of my colors here, which one of these carbons is going to get the bromine, the orange or the green? Right, less substituted one will get the halogen, the more substituted one will get the hydroxyl group. And they're going to go on opposite sides. So if I'm going to draw that bromine on a wedge, I need to draw that hydroxyl group on a dash. Whoops, bromine on the wedge, hydroxyl group on the dash. And what else am I going to have to do to be good? I got to change that methyl group. Make sure it's pointed in the opposite direction of that other bond. Is this a meso compound? No, definitely not. I got these two distinct bonds here. Your halohydrins cannot be meso. So I'm going to do another one here where I flip all my dashes to wedges, showing my stereospecific products. Cool. All right, so we got these two new reactions here, two new addition reactions, a hydrogenation reaction where we're adding hydrogens to either side. This does not have any regioselectivity since those two bonds are the same, but it does have stereoselectivity. It is a syn addition. And then our halohydrin formation where we're adding a hydroxyl group and a halogen about our double bond. This is a regiospecific reaction in that my hydroxyl group gets the more substituted carbon, and also stereospecific in that those two new bonds are going to go on opposite sides. All right, we're going to end with one more that we'll sort of pick up with next time as well. This is a fun one here, and I know they've all been a lot of fun, all right? But this is what's called an ozonolysis reaction. And this one's a little bit different than all the other reactions of alkenes that we're going to talk about in that it is not an addition reaction at all. It is what's called an oxidative cleavage reaction. All right, and since it's not an addition reaction, we're not going to have a mechanism for it. We don't have to worry about regioselectivity, and we don't have to worry about stereoselectivity. All right, so these are just reactions that we should be able to predict our substrate reagent product combinations for. All right, so let's do an example here of an ozonolysis reaction. All right, if we take an alkene and we treat it with ozone, O3, all right, there's a second step where you treat it with what's called dimethyl sulfide, DMS. I'll just draw that structure in case you're curious, dimethyl sulfide. All right, again, what happens is what's called an oxidative cleavage reaction. We are going to chop this molecule in half at that double bond. All right, so what we're going to do, and I'm going to color these fragments here, is we're going to take this 5-carbon alkene and we're going to break it up into these two pieces. One piece will have 2 carbons. The other piece will have the 3 carbons, right? So we've broken this molecule into 2 parts here. Okay, and this is an oxidative cleavage reaction. So what happens is we're not going to gain an extra carbon somehow. Instead, an oxygen from that ozone is going to be on the end of that double bond, right? So we've created these 2 new carbonyl groups here. All right, importantly, my counting carbons still works, right? I should have 1, 2, 3, 4, 5 carbons on the product side. 1, 2, 3, 4, 5, right? We've just taken this molecule and chopped it right at that carbon-carbon double bond. All right. So this is these examples that I want you to sort of copy down and try to work through before the beginning of next class period. And this is where we'll pick up with next time as well. All right, so you can go ahead and copy down these 3 examples. I want you to try to work on them on your own before next class, and that's where we'll pick up with our lecture on Thursday. All right, we are officially entering into the challenging portion of the organic chemistry course here, right? We spent a lot of time just kind of learning about how to draw molecules and these various features, and now we're learning functional groups that have these reactions associated with them. And this is very much so what the remaining part of this course, as well as what the second semester of the course looks like. Functional group, how to name it, reactions of those functional groups, right? Your best friend in the world is going to be studying this material a little bit throughout the week, like a little bit every day, rather than trying to cram it all at once. It's just way too much information to fit into your brain in one cram session. Spacing out your study time is going to be your best friend in learning this material. What's up? The mechanism? Yeah. Oh. Hold on. There we go. Yep.